go. So welcome back, everybody. Happy Thursday. Yay, Thursday. Not quite Friday, but we can pretend. Let me move this thingy out of the way. So I wanted to point out that I had to push some stuff back in the schedule. So we're going to be spending at least another week on these models, and whatever we don't get through by the end of next week, I'm going to make separate videos for offline. I had intended to do that for example 6C anyway, because it's just a SAS specific example and it's not something I'm asking about in homework. Or 6D for that matter isn't going to be covered in homework either. So we will get caught up eventually, but I did post some new stuff. Lecture 7's A is a review and B is time invariant predictors. So you can have a look at those. And also your next formative assessment, here we go, April 5th is due on before Monday. So something to work on. And then homework 3, which is in progress, is due the following Monday. So any homework questions have come up so far? Homework 3? Not yet. I know it's early, but you know, I have to ask. Office hours as usual if anybody wants to come hang out and work on it. So that's totally fine. We'll yell at R together and bond over our shared frustration with technology, things like that. Then if not, let me see what I want to start with. Let's start with quadratic stuff. Yeah, we're going to do some quadratics. Let's start there. Page 9 of example 6A is where we are. So this will be the last part of homework 3 that we will get through today. Adding squared time as a predictor, first as a fixed effect and as a random effect. So conceptually, what am I doing if I'm adding squared time? What's the point? What am I looking for? I'm watching the chat window, or you can talk. Yeah, acceleration or deceleration of change. So change that speeds up or slows down. I'm going to get it right today. We are not slowing up and speeding down today. The change in each occasion's slope, yep. Acceleration or deceleration implies a constant change of the slope for the effect of time across time. Nonlinear trajectory, yep, also true. Quadratic implies a particular flavor of a nonlinear trajectory, which is a U-shaped trajectory. So the linear and quadratic slopes for time work together to describe one of 4 kinds of trajectories. Remember the 4 kinds? You have a positive slope that speeds up, a positive slope that slows down, a negative slope that slows down, or a negative slope that speeds up. It's going to be one of those 4. So we just have to figure out from the sign which it is. So if I'm adding a fixed effect first, like I have here on page 9, I'm asking if on average there is an acceleration or deceleration of the trajectory. So on average, does the line need to have this bendy U-shaped aspect to it? So to do so, I'm picking up beta 2 here in the level 1 equation. Because I am picking up a beta 2, I have a third level 2 equation. So at this point, the third equation is sort of silly because all it has is a fixed effect. But in keeping with the system of notation in which each effect at level 1 becomes an outcome at level 2, potentially, we keep it this way. So gamma 2O is the new term that I've added. Over here on the right box, you can all see this, right? We're good? Yes, we can see it? Okay, good. Had some internet issues earlier with the first class, so, and I can't even blame my kid or my husband for hogging all the internet today. It's on me at this point. So this box right here is summarizing how the model predicts what the mean outcome is supposed to be at each occasion, as well as how the model predicts what the linear rate of change is supposed to be at each occasion. Both of those can be found as linear combinations of the fixed effects. So the equation for how one would create y hat, a predicted outcome from the overall U-shaped trend, is the fixed intercept, gamma 0, 0, plus the fixed linear slope times time, plus the quadratic slope times time squared. And so this equation right here, this first one to calculate the predicted intercept, is what shows up in this set of estimate statements in SAS, corresponding LinCom statements in Stata, and in R, of course, the first set of these contest 1D things, where the values that are being plugged in correspond to the multiplier of the fixed effect in the equation. So the fact that every occasion needs a fixed intercept no matter what is why there's a 1 after the intercept or the constant and in the first set of zeros in R. Then the value that shows up otherwise is what the time predictor is coded at for that occasion. So if I want session 1, I have coded time such that the 0 value corresponds to session 1. So time 0 goes with session 1. So including that in the label to hopefully make it less confusing as to what is being referred to. Cough, cough, homework question. Okay, with me so far? So this is a convenient way to recognize what the model is saying your trajectory looks like, and we're going to compare it to what the right answer is given by what was found in the saturated means model to see if it does a good job of describing the distances between the means across time. Now the tricky one. Instantaneous linear slope at each occasion. So we have a trajectory that is response time coming down over time, so people are speeding up how quickly they can do this task with more practice, but the rate at which they are declining is slowing down. So there's a deceleration. That's a typical learning curve. So I got my prop here today. Do you remember this? I don't have it out very often. This is a telescoping pointer stick. I highly recommend you get one of these. They're a lot of fun. Plus you can poke people who start sleeping in your class. So it's very effective for that as well. Not that I've ever done that. Actually, I have. But so if we start with a slope at the first occasion, the slope becomes flatter as time goes on, as you sort of come down the U. And so what this second little equation here is asking for is what the model says the slope is at each subsequent occasion. And the trick to getting this right is the 2. Twice the quadratic fixed effect, the fixed slope, is how the linear slope changes per unit time. So to get to what the linear slope would be at any occasion, we start with what it is at time 0, which is what the fixed linear slope is telling us, and we add to it the contribution of twice the quadratic slope coefficient as a function of which occasion we want the predicted linear slope for. So the second set of estimate statements then, where I just have time and time squared, the values that are multiplying time and time squared, the 1 is because each linear slope at a minimum starts off with what the linear fixed slope is going to be at time 0. Then the numbers that show up after it is the value of the occasion for which you want the prediction. So I want the linear slope at time 0, at time 1, at time 2, at time 3, multiplied by 2. The 2 is the trick to this, because the quadratic coefficient itself, gamma 2O, the fixed effect, tells you half the rate of acceleration. So you have to multiply it by 2, homework question, to get the right answer. So that shows up then in the Stata code right here, and in the R code right here. Okay, questions so far, or any of that you want to hear again? We're good? So far? So far, so good? Okay. Let's see what happened. So just as a reminder, the model for the variance at this point has only a single residual at level 1 whose variance is assumed to be equal across time. So this is the diagonal structure that is usually assumed to be true for these models. You can add to it, but we're not doing that right now. Do that in a minute. We got a G matrix. G matrix is, question, quiz time for you. G matrix is level 2 or level 1? Finger question. G matrix, level 2 or level 1? Oh, the 2s have it. Very good. Yeah, G matrix is the variances and covariances of your U random effect terms. 1 U per person, so this is between person variation, which makes it level 2. So all the reasons why people differ in their predicted response time at time 0, that's my random intercept variance. My random linear slope variance tells me all the reasons why people decline differently. So in this data set, everybody's going down for the most part. The extent to which that is true for any individual differs across people. Good. And the intercept and slope happen to be correlated this much. And keep in mind that if you want to interpret that correlation, you'd have to talk about the intercept at time 0 specifically, because if you center time anywhere else, that correlation is going to change. So those parameters put together give me my predicted V matrix, which is the composite total marginal prediction by the model. And if you're ever uncertain about how many parameters you have in your model, here's the trick. Count them up. Every row in this table right here is a parameter in the model for the variance. So this model is a random linear time slope, random intercept, their covariance, and the residual variance at level 1. Those are the 4 that we've got that then work together to create the overall pattern. In this case, the null model likelihood ratio test does not tell us anything helpful. It tells us if we need any kind of G matrix at all. So the 3 parameters that are listed as the degrees of freedom are the 3 parameters in the G matrix: random intercept variance, random linear time slope variance, and the covariance. So that's not really a useful question, but it prints it out anyway. So we have our new fixed effects. First question, is my fixed quadratic time slope that I just added significant, and how do I know? Where do I look for that? Is the fixed quadratic time slope significant? Where am I looking? Yeah, this is the softball one. Yeah, p-value. This one. Fixed effects. You can stare at the p-values. Nobody's going to argue with you about that. The reason is because fixed effects have a null hypothesis of 0 and are unbounded. They can be positive or negative, so we don't have to worry about boundary conditions, any of the stuff that we have to worry about for variances. So in this case, here is my new fixed quadratic slope. So let's put it all together. 3 fixed effects in the model. So just as you can look at the other table for the number of parameters in the model for the variance, you can look at this table for the number of parameters in the model for the means. 3 fixed effects. Intercept, gamma 0, 0. That tells me what the model says my outcome is predicted to be at time 0. It's not the actual time 0 mean. It's what's predicted by the curve. So it's going to be off a little bit. According to the curve that is predicted by this quadratic model, at time 0, which is session 1, people are predicted to spend 1945 milliseconds on this task. That's my initial starting point. Time 1 here. Can I just call this the linear time slope? The rate of change in as a function of time is a decline of 120 milliseconds per session. Can I call it that and be done? Note the uptick in my voice, which is a key. Yeah, at time 0. Yes, this is conditional. It is only the linear slope at time 0. And so you have to know where time 0 is to be able to interpret it. Time 0 is at the beginning. So if I have my U-shaped trajectory, it's the first slope at time 0. That slope is 120 milliseconds a session. It is the slope of the line that is tangent to the curve at that point, otherwise known as an instantaneous linear slope. The second you move off of time 0, the slope starts changing. So which of the 4 is this? Now I'm pointing at my monitor, like this is going to help you. Old habits die hard from the classroom experience, right? So what is my quadratic coefficient doing to my linear slope? Yeah, it's speeding it up or slowing it down. What's it doing? Let's take a vote. We got 1 vote for slowing it down. Yeah, this is a finger question. Yeah, slow it down or speed it up. Yeah, it's slowing it down. Yeah, anytime the signs are an opposite, they're working against each other. So it's a negative slope that is becoming less negative, is the way that I would describe that. Or in layman's terms, it's slowing down. The rate of improvement, that's what negative slope means in this context. So if you write a paper in which you say the negative linear slope became significantly less negative over time, I guarantee reviewer 3 is going to be like, what the hell is that? It's like, no, we got to translate that. Like in stats language, that's how I think about it. Yeah, it's a negative slope that's becoming less negative. Okay, let's put my GRE hat back on and use some words. Negative slope is my rate of improvement. So the rate of improvement is slowing down. The rate of improvement is diminishing. Can you give me some other words besides slowing down? The rate of improvement is abating. Can I say that? Yeah, once upon a time I knew words. Most of them have left to make room for this stuff though. There's only a finite amount of space up there. But yeah, this is a negative slope slowing down. So what is happening is that this linear slope of minus 120 at time 0 is decelerating, I would say that, by how much per occasion, and don't say 13. By how much is the linear slope slowing down per occasion? 26. Yes, twice. You got it. Well, more like 27 and some change, but we'll make SAS do the math for us in just a second. But yeah, twice. Twice the quadratic is how the linear slope changes per unit time. So that's where the estimate statement results come in handy to help us break that down. And because I want you to like me, I wrote out the equation for how these numbers came from. This is not SAS being nice to you. This is me being nice to you. Question, what if the time intervals differ? It doesn't matter. So there is an overall smooth continuous function that the model is creating, and that function can provide the predicted outcome and the predicted linear time slope at any point in time. So you could ask for it at time 1.73 if you wanted to. And that is implied by the model because it's all one function. So in this case, I only have 6 discrete occasions, but I could have asked for it for any in between if that was a possibility for my measurement schedule. So the intercept 1945, that's what's given directly by the model. The predicted outcome, so a conditional intercept or a conditional mean at each subsequent occasion, then is given by the combination of the 3 fixed effects. And then the linear slope at each occasion. So it's minus 120 at the beginning. It slows down by twice the quadratic coefficient. So that's where it's minus 120 plus, or yeah, I'm going it backwards. Yep, plus the 26, plus another 26, plus another 26, plus another 26. So this gives you not just what the linear slope is predicted to be at each occasion, but it also gives you how precise that is. So note the difference in the standard errors here. They are always going to be smallest near the middle. Because if you think about just even like a linear slope, if you wiggle the slope what happens in the middle changes a lot less than what happens on the outside. So the inside is going to be tighter. And we also have a p-value. So I could potentially use this information to plan my next study. How many sessions, for how many sessions, should I say, is there significant improvement being predicted? P-values. Session 1, they're improving. Session 2, they're still improving. 3, 4, 5 is where it sort of shuts off. So by session 5, the rate of change is no longer significant. And look at what happens at session 6. Positive slope. Now, is that weird or a consequence of the model? Or both? I guess those are not mutually exclusive options. Yeah, a positive slope in this context means response time would be predicted to increase, meaning they're getting worse at the task. Yeah, consequence of the model, because we're riding the U down to the bottom, and the model predicts it goes back up again. So it's creating like a J kind of shape where the tail end is starting to come back up again. So for that reason, this model might be theoretically dissatisfying because you wouldn't expect as a function of learning that people start getting worse again. Now maybe they get worse again because they hate doing this task and they quit trying, but that is a different phenomenon, right? That is the lose your will to live effect, which is a separate psychological process than processing speed. And then pseudo R-square effect size. So I did, relative to the previous model, we have captured another 6% of the level 1 residual variance by adding the quadratic effect. So not only is it statistically significant, but it has captured 6% of what we used to call E-variance. All right, questions, comments?
So, I have a question.
Yeah.
What if like a linear term is not significant, while the quadratic term is significant? In that case, simply like it's gonna be just v, like which is not going up or going down.
Mm-hmm. So in that case, like if you have a straight, like for instance, a U, like a full U, you would still need to keep the linear term even if it's not significant.
Yes, sure.
Mm-hmm.
Okay.
Is that your question? Whether you...
Yes.
Mm-hmm.
So that case, especially like I'm wondering, like how we should kind of interpret so, because like at least like if linear term is like significant in positive or negative way, like we generally say like it's kind of increasing or kind of decreasing, right?
Mm-hmm.
But if like a linear term is not significant, but only quadratic term is significant, like I'm just thinking like how we can, what kind of things we can say, like our model says like how we can say about the possible effect of x on our dependent variable.
So in that case, if at time 0 the slope is non-significant, so it's functionally 0, then the direction of the quadratic would tell you where the function is headed. So from that point, if it heads up, you'll have a positive quadratic, or if you head backwards, it would be negative. Like that could happen. Let's say that I decided to center time at the end of the study, right? I made session 6 my time 0 so that I could predict where people ended up as my model reference point. That's a common thing to do. Had I set up the model that way, then my linear slope would indeed not be significant, because by session 6, the slope is non-significant. But if I move backward in time, the model predicts that response time would get higher as I moved backward in time. So I think you can still talk about it the same way. You just may need to refer to a different occasion as a reference for where the function is headed.
I see. Okay, great.
And then whether you'd move forward in time or backward in time depends on how you've centered the model.
I see. Awesome. Thank you.
And if nothing else, make a picture, by the way. That's going to be the next thing. Make a picture. Don't make your readers work that hard. Okay, did I hear another question?
I was about to ask something.
Yeah.
The 6% of the e-variance,
Mhm.
I was just wondering about, like, so we were talking about how adding a quadratic parameter like adds so many, you're adding so many more parameters by including quadratic time. If you're only, is that not true?
One by my count.
Oh, okay. I was thinking about, maybe I just meant time in general then. Okay, that makes sense.
Yeah,
I get
one more fixed slope.
where I was going with that, maybe it still applies, is when you're talking about like us, like I was just wondering in like the real world, when you have, it's like a somewhat small amount of variances being accounted for and you're having to add on all those extra parameters, how do you make those decisions? Is there a place in which like it'd be appropriate to say, you know what, I'm not going to include this parameter because it doesn't decrease the variance by that much, I think I still get like accurate p-values and that way I can do with less parameters?
Yeah, if you're in the situation where you have a ton of power, you have a ginormous sample and everything is significant, then adopting some sort of cutoff based on effect size, I think, is a reasonable thing to do. I don't think there are clear guidelines as to what that cutoff should be. So you may have to make a judgment call or dig in the literature and see if you can find someone to cite who did something that you like and therefore it's an established method. But I do think that is a reasonable thing to do. The catch in these models though is that it's not 6% flat across the board, right? It's 6% of the e variance that was still there after adding the fixed and random effects that we already have.
Hmm.
And so it's 6% actually sounds like a lot, but it's not a lot from that perspective of what is the total that it could have been. It's not a lot of
Yeah.
absolute information that is in the level one residual variance. Like if we look at the numbers here, I don't have a proportion because it doesn't make sense in the same way to add it all back together again once you have a random slope. But if you just look at the numbers, the residual variance is 26,000 and some, but the random intercept variance is 254,000. Like it's a lot. There's a lot more information elsewhere than the e's.
Gotcha.
So
Yes.
yeah, it's not a great answer to your question other than it's complicated to talk about only effect size. But I do think that is a reasonable strategy if you are overpowered in the real world. Okay, other questions? Let me find back to where we were here. No? Okay, so then the next question, do people accelerate or decelerate differently? Does the fixed quadratic time slope that I just added need to be random also? So in making something random, you keep the fixed part and you add on the random part. So we have kept the fixed slope in the model and added in the equation here u2. U2 is going to be the individual deviation of each person's quadratic from the fixed quadratic. And that shows up here on the random line. So I'm adding quadratic time as a predictor on the random line as well as on the model line. So it stays as a fixed effect. You add it as a random effect also. There, of course, across the three programs, what the code looks like to do this differs. Fun times. So in Stata, every time I tried to put time1 hashtag time1 in here, it yelled at me and said, you can't do that. I said, okay, fine, I'll make time squared as a variable and put it in. And then it said, yeah, you can do that. So that was my solution to the problem, is to just literally make a column in the data set that was time squared and put that in as a random effect, even though it's just fine making it for me as a fixed effect. Is there a reason why I have intercept capitalized in the SAS code, or is that just to keep your own things straight? It is just to keep my own things straight. So one of the reasons why I hate case-sensitive programs or programs that insist you use lowercase is because my own coding convention is to put dedicated keywords that are SAS commands in capital letters and to use lowercase or title case for names of variables or things that I would change. So I have intercept in capital letters here for my own edification, that is a SAS recognized term, that it is going to build for me a column of ones to represent as a variable and put it in there. If you don't type intercept, you don't get a random intercept, whereas that is a default that you get in Stata and in R. So it's fine for Stata to do a fixed, yes. And this may be something where somewhere on the internet, someone listening to this will solve this problem for me, but I figured out how to solve it by making a variable. So it made it work. The R code will let you do that. What does I mean? Can anybody tell me that? I think it means do math. That's my best guess. But I found someone else's example where they had done it this way, and it seemed to work as a fixed effect. So I time 1 and then the caret to be squared. In the random effect, you can use the same thing and it was fine. Indicator? Does that mean like make a new variable?
I mean, they use this formulation I know over in biostats. I haven't seen it in code, but when they're writing out formula, they use generally the I for certain variables.
Okay.
And it's usually to stand for like a categorical indicator, so I didn't know if it was the same.
Well, in R, that's factor instead, and this is not a categorical variable. So I don't know. It's I. I because it said so and it ran. So welcome to Google University. That's where we're at when it comes to R code. So once you figure out how to get your software to take the time squared variable as a random effect, then you're home free. Except, I found that the same model for this data and in your homework data, by the way, in Elmer, threw a convergence error. And when I reran it in LME, it did not. And it gave the same results as SAS and Stata. So Elmer appears to have more difficulty, at least in the 2 instances that I've tried, with random quadratic models, and I do not know why that is, because it's supposed to be more computationally stable than LME, but I have found the opposite. So the instructions on your homework ask you to re-estimate the random quadratic model in LME in R to make sure that you get the same answers as given in the other programs. So here's a question, finger question for you. You ready to play along? Like we're on a game show. That's what I feel like office hours is a lot of the time, is like my own personal game show, because I have people asking me questions about all these different things and I'm like, hit the buzzer. Yes, I know that answer. But here's a game show question for you. I added this one thing, right? I added a variance for this U2. How many parameters did I just add to my model? And it's not 1. In asking for a new random quadratic slope variance, the variance of the U2s, how many parameters did I also add? We got 1 guess for 2. 2 total or 2 also? 2 also. We got another guess of 4? Question mark. Yeah, so we got 1 variance. The correct answer is 2 more, 3 total. Because every time that you add a new variance into your G matrix, you are also adding covariances with the stuff that was already there. So 1 variance and 2 covariances were added for a total change of 3 new parameters in the model for the variance. And I have an easier way to remember this. A mnemonic that I have created for this. The correct answer for the change in the model degrees of freedom when you add a random effect is equal to the number of random effects you now have. So let me say this differently. If I go from a model where I add a random intercept, now there's 1 thing on the line, that's one degree of freedom. If I then add my random linear slope, that's 2 things on the line, so that's 2 degrees of freedom. If I add in my quadratic slope, that's 3 things on the line, that's 3 degrees of freedom. If I were to add a cubic slope, Then how many parameters have I added? That'd be 4, because there's 4 things on the line. So you're always adding one new variance plus covariances with all the terms that are already there. That is what type U equals UN gets you, and covariance unstructured in Stata. But we're not going to have a random cubic today, just quadratic. So that is relevant in conducting significance tests for the new variance. Anytime you add something to the model for the variance, it's a likelihood ratio test. But you have to know how many parameters you've added as the degrees of freedom for that test. So in adding a random quadratic time slope variance, you have also added a covariance with the intercept and a covariance with the linear slope. So I have highlighted then in the output the 3 new terms in the G matrix. So 634, column 3, row 3, that's my new quadratic random slope variance. And then the covariance with the intercept and the linear slope are adjacent to it in that 3rd row. Question, can you not do a likelihood ratio test for fixed effects? You can, but not in REML. If you want to do a likelihood ratio test for fixed effects, you have to be in ML. And if you're in ML, you are going to underestimate your random effect variances and covariances in small samples, and therefore the standard errors for the fixed effects that go with them. So we do likelihood ratio tests only for the model for the variance as a consequence. All right. Questions so far? So the new pattern that is created in my V matrix, what the random quadratic time slope is doing behind the scenes is allowing a 3rd source of person dependency, which is a non-constant source that is a function of time to the 4th power, actually. So the diagonal of this V matrix right here, where that came from, is that ugly thing, where t is time. So the random quadratic time slope model predicts that variance changes quartically. Can I say that? Time to the 4th power, quartically. Am I making up words? Can I get a judge's ruling from math people here? Quartically? I don't even want to know what the transcript thinks I just said. You think you're making up words. Okay, time to the 4th power, then. Fourthedly, quartically. And the covariance, the off-diagonals of the V matrix, they are this ugly thing right here. But at the end of the day, the goal is to find a pattern that best matches what we got in the unstructured matrix, in which all the variances and covariances get to be whatever they want, a pattern that does that with fewer parameters. Another vote for making up words. Okay, well, I don't have a problem with making up words. I just like to know when I'm doing it. Later in the semester, you will hear me make up a word, extrapolable, but I need it. So it's a word to me. Anywho. So this is an ugly pattern, but this is what the model says the V matrix looks like as a function of time. And so you'll note that it lists it specifically for person 101, because by default, when you ask for V to be printed, it does it for the first person in the data set. That means it's going to use that person's time values in showing what the model V matrix is predicted to be. You can actually ask it for any person in the data set's V if you have people who are measured at different times and you want to see what the impact of that is on the pattern. V-core then, correlation version of the same matrix. And here are all of my new parameters. So those 3 lines in the covariance parameters table give me the variance of the random quadratic time slopes and their covariance with the intercept and linear slopes. I have a likelihood ratio test coming up here to judge the result. So this test says yes, let's keep it. The -2 log likelihood went down, smaller is better, by 38. So div, that's my test statistic for the change in -2 log likelihood. On 3 degrees of freedom, it gives me a p-value that is 0 to 8 decimal places. So yeah, we keep it. So conceptually, it looks like people need their own random time slopes. If I want to do an effect size, I'm not going to do pseudo r-square because I haven't explained anything. What I have done is introduce another pile of variance. So there's 4 total now. So instead, I'm going to do random effect confidence intervals. So you'll get a chance to practice this on your homework. I don't even have to cough. I can just say that. I have a spreadsheet that does this for you. I don't have a macro or anything yet, but I have a spreadsheet. I'm sure you can find some way to do it in R automatically as well. But each of these confidence intervals then, there is one for every effect that has both a fixed effect and a random effect. So in this model, there are 3: intercept, linear time, and quadratic time. So the center of the interval is the fixed effect. The boundaries of the interval is given by the square root of the corresponding variance. So random intercept variance in computing the CI for the intercept, random linear time slope variance in computing the CI for linear change, and then random quadratic variance for computing it for quadratic. And so then putting this together, how much variance is in our model? Well, at time 0, 95% of my cases are predicted to have response times anywhere from 900 milliseconds to 3 seconds. That's a pretty big difference in terms of the scale of this type of behavior. At time 0, the linear slope is predicted to be anywhere between minus 436 milliseconds a session all the way up to positive 194 milliseconds. So some people are actually predicted to be worsening initially. And then likewise with the acceleration, some people are predicted to accelerate and other people are predicted to decelerate. It makes it harder to put these together when both of these have different signs potentially. And reviewer 3, is it a problem that these two overlap 0? Yeah, I don't think it's a problem. It doesn't mean that my fixed effects aren't significant. It means that there is such amount of variation around them that the slopes are predicted to change directions in certain individuals. So, all right, questions or comments? How are we doing? Thumb sideways emoji, at least. Yeah, we agreed that we need to add a thumb sideways and a thumbs down emoji to have a complete reporting of one's feelings in the Zoom. Otherwise, a thumbs down can be the surprised face. Like, bad. So everything we've done up to this point has been focused on making the model better. We start with an empty model with the random intercept. We added fixed linear time. Did that help? Yes. We added random linear time. Did that help? Yes. Quadratic time. Did that help? Yes. How do you know when it's good enough? How do you know when to stop? And Jing is telling me to speed up. I had to click on it to see what is that saying. Oh, I can't tell you that I don't like it, but I can tell you to hurry up. Man, that seems harsh for the Zoom. Or slow down. Yeah, smack talk Zoom style. Speed it up. I got a life to lead here. So question to you. How do you know if this is good enough? Because I could add cubic time, right? I've got 6 occasions, so I could add up to time to the 5th power as a fixed effect and time to the 4th power as a random effect if I wanted to. You don't know how to turn it off? Okay, well then I won't be offended. It'll just keep telling me to slow down or whatever it's saying. How do I know when to call it good? Yes, it's tricky. Likelihood ratio test against what? I gotta have a standard for what good enough is. Do I have a standard? Against the best. Yeah. What's the best? The most complex and worked down, yeah. So the best fitting model is the one that has the most possible parameters saturated. So saturated means is the right answer for what the trajectory is predicting, and unstructured variances and covariances is the right answer for what the random effects are predicting. So that's my answer key. So complicating matters is when we are using REML estimation, which is what we have here, we can't directly compare our model against the best model. Now, question, why not? Why can't I just do one more likelihood ratio test and call this example done? In REML, why is that not allowed? Yep, we've changed the means and it's only for the variance. Same answer, two different ways. Yeah, the right answer has different fixed effects. So because we're using REML, we can't directly compare it. And the solution to that I adopted in the textbook was to switch to ML and do it again and then make a comparison. But I have a better idea that I've come up with since then. So I wanted to show you that idea, although you do not yet have to do this for your homework. So the last model that I have here sort of heading forward is looking at the assumption of the diagonal R matrix. So the assumption that the residuals are uncorrelated. I tested that by adding an AR1 correlation to the R matrix. So on the repeated line here, I changed the type from VC to AR1. I also changed the residuals to AR1 in Stata, and in R, I had to switch back to LME to do this, adding in this line right here that adds an AR1 correlation. Here is the corresponding R matrix that I was given. R core gives me the R autocorrelation specifically. So the new model says that the residuals for adjacent occasions are correlated 0.17. I can find that entry right here. It's not significant according to this Wald test, and it's not significant if I do a likelihood ratio test. And note that the p-values for these two tests are similar, but they're not the same. Likelihood ratio test is supposed to be the more trustworthy version. So yeah, adding that doesn't help. So the question is it good enough? So to get a sense of what the following tests are assessing, what does it mean to be good enough? Does our model accurately capture the data with respect to time? First, the fixed effects. So this is a picture that I made. This is from the book that describes what each of the models in this handout predict with respect to the means over time. So we have the solid black line with the squares. That's from the saturated means model. That's the answer. We have the empty model, the flat line here that predicts no change. We have the linear model, which is the straight line here with the triangles through it. So you can see that's not a good one. That doesn't look like it fits at all. The quadratic model is the bendy one with the diamonds. Now, how do you think that did? Not bad, right? It looks pretty good. There's a little bit of a bumpiness here. It's not a perfect quadratic, but it's a reasonable approximation. I know that it's better than fixed linear because adding quadratic helped the model. But based on the reasonableness of this fit, I probably wouldn't try a cubic effective time. Doesn't look like it's warranted. I did want to highlight, though, theoretically what each of these models suggests is going to happen if I were to add another occasion. And so I plotted out these trajectories out past session 6 out to session 9. The linear model predicts that response time continues to decrease at the same rate forever and ever. The quadratic model predicts it's going to come back up. So from a theoretical perspective, neither one of these is great. But if we just look at the fit of the model to the means, what I need to do is to find a way to add in the extra parameters that it would take to get from quadratic to saturated. So that's where the dummy code variables that I created at the very beginning of this handout come into play. Cubic is an S shape rather than a U. Yeah, it doesn't look like it's an S, so I'm not going to go there. So in anticipation of answering this question, is my quadratic good enough for the means? I created these session-specific dummy codes. So you do not have to do this on your current homework. I think you're going to have to do it on the next one, though. We're going to have to see how all the programs cooperate. So I have S1 through S6, which are dummy codes flagging each additional session. I have 6 of them because I have 6 occasions in this example. I am going to take 3 of them. Let me find back where I was. And add them to the model for the means. Okay, so skipping the second picture for now. I'm on page 18. So the question I want to answer, is my quadratic model good enough to describe the mean trajectory? I have 6 occasions. That means I have 6 means. How many parameters did I spend in my model for the means? How many fixed effects did I spend to create my predicted trajectory? 3. So that means how many are left over? If I have 6 means and I've spent 3 parameters to recreate them, how many are left over? Yeah, I'm not trying to trick you, I swear. 3, right? Because 3 plus 3 is 6. So I got to fill them in. In order to test whether or not my quadratic curve fits my 6 means, I need to find a way to add in 3 more parameters and see if they help. So that's what I did. I added in 3 dummy codes. I'm going to do this 2 different ways to demonstrate in this model that it doesn't matter. But I added in an effect of whether or not it's session 1, whether or not it's session 2, and whether or not it's session 3. And so now, adding in the fixed intercept is the one that's actually here but not listed. I've spent all 6 parameters. So my question is, did adding these 3 terms help? If so, my curve doesn't do a good enough job. So 3 new fixed effects representing each of the remaining degrees of freedom by which my predicted trajectory differs from the mean trajectory. The other piece of this is to lump them together. So contrast statement. You will have seen this before if you had 6242 with me, or if you had generalized models. Test statement in Stata does the same thing, and contest MD. What these statements do is lump together a set of fixed effects of your choosing. I'm lumping the 3 new dummy codes to see if they matter. If they matter, then my model doesn't fit. Does it matter which 3 you put in? In this model, no. So I'm adding in the first 3. I'm asking for a joint hypothesis test of those 3 new fixed effects. And here's what I found. Wah, wah. That's a technical term. So a significant p-value in this case is bad. This is very much analogous to why a significant p-value is bad in structural equation modeling. It means your model doesn't fit. It means there was something to be gained by adding in these 3 new fixed effects to literally plug the holes in the trajectory. relative to what the actual means are supposed to be. Womp womp is a technical term. If I could, I'd have a sound effect right here that's from The Price is Right. Doo-doo, doo-doo, doo, like that sound. Yeah. Womp womp, not to be confused with womp there it is, which is a joyous expression as opposed to a sad one. But yeah, womp womp, technical term. The fact that I have my p less than 0.05 means adding those three contrasts helped the model, which means the quadratic is not doing a good enough job. By the way, I have asked for both a chi-square and an f here to illustrate how they relate to each other in case your software only gives you one or the other. F times numerator degrees of freedom for the number of slopes that you've lumped together is your chi-square. And then each has a different p-value associated with it because F uses denominator degrees of freedom, whereas chi-square does not. So F is going to be more accurate. In a big enough sample, they will converge to the same answer. And to answer the other question, does it matter which three they are? I put in the other three. Dummy codes for session 4, 5, and 6 instead. And as expected, I get the exact same significance test. So in this model, it does not matter. Okay, does that make sense? You can think of it as, you get back to the picture up here. I am trying to fill the holes, the gaps between the predicted trajectory and the real one. And if I add 3 new little increments to the trajectory, I can get from my 3-parameter trajectory up to the 6 means trajectory. In SEM context, this would be accomplished by freeing the intercepts for 3 of your observed variables. They would then be available to fill the gaps between what the model says and what the data say. In a new piecewise article example that I added to your reading list, to Leo et al., a former student's project, by the way, from this class, we had to do that because he had a piecewise model that did not fit exactly, and so we had to fill in some of the holes where the piecewise model whiffed on the trajectory. So quadratic doesn't do a good enough job. It doesn't look like cubic is warranted. I'm going to have to go to a different approach. What models would it matter, or I'm not sure. It matters in models that are partially saturated and partially not. Then you cannot add dummy codes for the part that's already saturated. So that occurs in piecewise models, which is the next set of examples that we have to go through. So means model doesn't fit very well. Variance model, I know it's kind of strange to look at, but you can do the same kind of visual inspection. What this plot is showing, this is the bottom figure, is on the y-axis, the total variance at each occasion. So there is a right answer for that as well, so long as you have a model with balanced time where you can estimate the unstructured model. So the black line with the squares is the right answer. From the unstructured variance model, that is what the data say the variance at each occasion should be. The flat line in the middle here is from the random intercept model. It says variance should be the same across time. Clearly not a good fit. The triangles, the one that looks bendy here, this is the fit from adding random linear time. A random linear time slope predicts that the variance changes quadratically as a function of time squared. So that's why it looks bendy and it's starting to come back up on the other side here. Whereas the one with the diamonds that looks all crazy, this one right here that's shooting off into the stratosphere, that's the random quadratic model where the variance is predicted to change quartically as a function of time to the 4th power, which is why it went nuts, and it's actually off the y-axis. The last one is so high. So we can ask the same question. Do these do a good enough job recreating the variance at each occasion? And not pictured, but the same question, do they do a good enough job recreating the covariance across occasions? And that is going to be a likelihood ratio test. The only catch is that we have to keep the model for the means the same to just focus on the variance side. So then going back to here, this is page 18, the very end. I have one more model right here, which is like a hybrid. So this model has the same fixed effects as the quadratic model. It has time and time squared. But on the variance side, it's unstructured. So this provides a comparison for what the best version of the model for the variance could be that I can then do a likelihood ratio test against based on my random quadratic model. So I fit that in SAS, I fit that in Stata, and then I realized that in R, I had to fit it in GLS instead of Elmer because it has an unstructured component to the R matrix, and that it won't do likelihood ratio tests across NLME models and Elmer models, and so then I had to re-estimate the final random quadratic model in LME to be able to use ANOVA to do the likelihood ratio test. So that had a separate step that I had to do, and here's the result. So likelihood ratio test tells me that -2 log likelihood from the random quadratic model is 8302. The new comparison model, where I let everything be what it wants in the model for the variance, is 8267. That -2 log likelihood went down by 35 on a difference of 14 degrees of freedom. P-value is significant. So what does that mean? Yay, thumbs up, or boo, thumbs down? Yeah, this is a wah wah. This is directly parallel to the chi-square test of model fit in SEM. They don't match. That's what I just found out. That what my random quadratic model said the variances and covariances should look like, the pattern that it predicted, does not accurately reflect the pattern from the unstructured model, which is the data. So swing and a miss on both sides with the quadratic model with respect to fitting these data. But these are real data. I don't actually know what the right answer is. That's what makes it fun. Okay, how are we doing? Okay-ish. There is a lot happening. That is a very succinct way of describing this class. Yes, there is a lot. If you have balanced data, all of this is possible. If you do not have balanced data, none of this is possible. So balanced data, remember what that means? Vocabulary check. What does it mean to have balanced time? Yeah, everybody's on the same measurement schedule. You have a same set of common occasions. If you have a common set of occasions, you can get the actual mean for each occasion, you can get the actual variance for each occasion, and you can get the actual covariance from each occasion. Then you have an answer key to compare your model to. But if you have a different set of occasions across people, if you have unbalanced time, you don't have an answer key model. So these sorts of tests of absolute fit are not possible if you have unbalanced data. In that case, you're just sort of stabbing in the dark to see if it's good enough and making pictures as to how the model corresponds to what you would have seen if you could have had balanced time. Like if you temporarily round time into convenient intervals just to make some pictures, that would be a reasonable way to proceed. But yeah, we don't have it. So one of the common misconceptions about these sorts of tests of fit. And actually on the Quantitude podcast, they talked about this. And I wanted to call in and be like, nuh-uh, Greg Hancock, you got it wrong. Like, multi-level modeling doesn't have tests of fit. Sure it does. They just don't get spit out as part of the output. But I just did it. I just did a test of absolute fit. And if I wanted to, I could take all of these chi-square difference tests and I could turn them into CFIs and RMSEAs and SRMRs and all that crap that you get out of SEM as well. All of it is predicated on having balanced data. If you think about what happens in SEM, if you have items, you have a box for item 1 and you have a box for item 2 and a box for item 3. That's the same as a box for time 1, as a box for time 2, as a box for time 3. And if you use any of the SEM tricks that allow unbalanced time, definition variables by which the factor loadings can vary across persons, then all the fit goes away. All of it's gone for the same reason, because then there is no standard covariance matrix to come back to with the right answer. So this is to say you have these nice regimented ways of checking whether everything is working the way it's supposed to, only in certain circumstances. Balanced time. So what's the conclusion of the analysis? Did we find one best model to explain the data? The answer is no. Random quadratic appeared to be relatively better than random linear, which was relatively better than random intercept, but no, it doesn't fit. Not good enough. Do I pack up and go home? Sorry, NIH. I know you just gave me $5 million to collect this longitudinal data, but it doesn't fit. So I gotta take a break then. No. We got some more options coming. So that's what else could this be is next week. And so we'll look at a few more alternatives for how one can describe nonlinear change, piecewise slopes, break it into different sections and fit separate slopes for each section, as well as truly nonlinear change, models that have exponential curves, either truly nonlinear models or hacks that you can do with log transform time. So yeah, we don't have a good model yet, but we will. We will get there. Foreshadowing, ... At least one of these is going to fit. But in your homework, which you can now do all I'm asking you to do is fit the linear and quadratic models, not to do any tests of absolute fit yet. Not yet. All right. Any questions before we call it a day? Ready to call it a day? Can we get a thumbs up on that? Yay for leaving class 5 minutes early, because we're all very tired right now and full of information. Yeah, me too. All right, then office hours start now. Let me know if you need anything. Do your formative assessment, and I will see you next week. Thank you.
Hey, Lisa.